You've written two solutions to the same problem. One uses a loop inside a loop. The other uses a hash map and a single pass. Which one survives contact with a million rows? Timing them on your laptop only tells you about your laptop. What you need is a way to measure an algorithm without ever running it. The obvious approach is to run the code and time it. But a stopwatch measures your hardware, your language, and whatever else is running in the background, not the algorithm itself. Run the same function on a faster laptop and the seconds change, but the algorithm did not. Clock time is not a property of the code. It is a property of the moment you happen to run it. Big O throws the stopwatch away. Instead, it asks, as the input grows, how many times does the busiest line of code actually run? That count does not depend on the machine. A single loop over n items runs n times, whether it's a phone or a server. The principle is simple to say and does enormous work. Count the dominant operation and ignore everything else. Here is a function that finds a duplicate in an array. It builds an empty set, then loops once over every item, checking and inserting as it goes. There are no nested loops and no recursion that branches. The busiest line is the loop body, and it runs exactly n times. The oracle reads this as linear time, and because the set can hold up to n items, linear space too. Plot the work against the input size, and each glyph becomes a shape. Constant time is a flat line. Logarithmic barely climbs because each doubling of the input only adds one more step. Linear rises in a straight line. Linearithmic, the cost of good sorting, is linear with a gentle upward bend. Quadratic curves upward fast, double the input, and the work quadruples. Exponential is barely usable past a few dozen items. Same input size, wildly different futures. This is why engineers reach for Big O constantly. A database lookup with an index is logarithmic. Without one, the same lookup silently becomes linear, and nobody notices until the table has 10 million rows. The same shape shows up everywhere. Compound interest grows like an exponential algorithm, and an epidemic without intervention does too. Big O is a shared language for predicting what happens at scale, before you pay for it at scale. Three mistakes come up again and again. First, constants matter at small n. An ON2 routine on 10 items can beat an ON log n, one with a heavy setup cost, even though the curves say otherwise for large n. Second, people say O when they mean θ. Big O is an upper bound, big omega is a lower bound, and big theta is the tight bound that holds both ways. Third, best case and worst case are a different axis entirely. Quicksort is ON log n on average, but ON2 in the worst case, and both statements can be true at once. Retrieval practice. Pause on each prompt if you need to. Two nested loops over the same n items, that is O of n squared, because nested steps multiply. An O of n step followed by an O of n squared step, run one after the other, still O of n squared, because sequential steps keep only the largest term. Having the remaining work at every step until nothing is left, that is O of log n. And building a set that can hold every item in the input, O of n space. Remember three things. Measure algorithms by counting operations, never by the stopwatch. When you simplify, drop constants and drop every term except the dominant one. And always state both time and space, because a solution that is fast but exhausts memory was never a solution at all. Before you cast any spell, you must know how heavy it is. That is the oracle's measure. Count the dominant operations, ignore everything else, and you can predict how code behaves at a scale you have never even tested.